Hello everyone. Some of you may remember me from the video of the Tesla Model S drive unit hacked, which is now over 3 years old. So I just wanted to do a bit of a follow-up what has been happening since then, because there have been a lot of theories based on your comments that I've either been kidnapped by Tesla or employed by Tesla or silenced in any other way. So that was kind of funny and very thoughtful from you. Thank you very much. Fortunately, nothing such happened. Life has been going on and I have some updates for you. So as some of you know, before I was working at CERN in the Particle Accelerator Laboratory here in Geneva, Switzerland. And well, it's been now a year and a half since situation changed, and we are now having our own company which focuses on electronic development, mainly in the field of electric mobility. So I'll try to present you what we've been up to in the last 3 years, and well, there will be some follow-up on the individual items I have here on the table, and the, let's say, more direct videos about the particular topics. This is not gonna be like a video log. I'm not very good with videos, so it's gonna be just a summary of what we've been up to. And well, just let me know what would you like me to talk about and what would you like to see, and I'll try to focus on that. Now, if we go back 3 years, what you've seen on the video for the Tesla Model S hacked was this board. This was the first motor controller that we've used with Tesla. It's already a second generation, so this is the UMC Drive 2, and well, it already has a younger brother that we've developed afterwards. So this was really mainly just a test platform to verify the feasibility of motor control. And this is its younger brother. So this is the UMC Drive 3. Now, what is this? If you haven't seen the video, pretty much what we've done is that we've taken a Tesla motor and we've replaced the original motor controller with our own hardware, just to demonstrate that you can do it, that you can run the field-oriented control on other, let's say, on a big manufacturer's hardware. So the video presented it on the Tesla Model S drive unit and also on Chevrolet Volt drive inverter. So that's our UMC drive platform. We've had some success with it. We've sold it to different customers for different applications, mainly for prototyping. We've done different Tesla motor conversions with it. I mean, our customers did. We just supply what's needed to make that happen. And well, we've got a lot of interest out of that. So that's pretty much been the start of the company. Just people asking us that they would like to make race cars with Tesla motors or use some other parts from electric vehicles. So we've decided to just focus on that and try to help with these projects, because we really find what you guys are doing very cool. And if we have something that can help you do that, it's even better. Now, since we've done a lot of work on Tesla and other platforms, we've actually managed to reverse engineer not just the hardware interfaces, but also the CAN bus, which is the interface that arranges all the communications between peripherals in the automotive world. So you can think of CAN bus as an Ethernet of the automotive world. And pretty much, if you could theoretically emulate all the other subsystems, then you can also tell the car and you can tell, for example, the drive unit to run in any other car as long as you tell it what you want it to do. So with that philosophy in mind, we've designed this. This is a new platform. This one is the VCU 2.0, so Vehicle Control Unit 2. And we've been using this platform to control different vehicle parts over CAN bus directly. That means without actually assembling it or modifying the drive units or charging systems or batteries. we've just used this platform to make it easier for our customers to, for example, convert a combustion car to electric drive. So this is the VCU2, and we've had a lot of projects with this platform. Some of them public, some of them not. I'll try to put some of these projects on our website and maybe link them in this video as well if I figure out how to do that in YouTube. But anyway, so this is the VCU2 platform. The point of that, as I said, is to make the conversions easier by reusing the parts as is, by using the original CAN bus that we've reverse engineered on different vehicles. For example, on the Tesla Model S or Model X and similar, we have the entire CAN bus decoded, so every single message on the car, we can work with that. Now, if you look on what we've been doing more recently, let's say in the last year and a half, we've kind of reoriented ourselves from just supplying systems to enable reuse of parts of electric vehicles into developing our own subsystems. Now, when we've been working with different cars, we've noticed that the charges are kind of a problem. It's getting much easier to get drive units. It's getting much easier to get, all the other pumps and batteries and everything else you might need. But high power charge is still kind of a problem. The best you can usually buy is between 3 to 6 kilowatts, and on the market outside there is very little outside of that. So we've decided to look into the charging technologies, and I think we've done it exactly at the right time because the silicon carbide came. Now, silicon carbide is a new switching technology. It's a transistor. Pretty much, silicon carbide is a process how to make transistors. For example, silicon carbide is of course used for other things, even for grinding. But what we are using it for is to develop higher efficiency power converters. Now, every electric vehicle charger consists pretty much of 3 or 4 main parts. That would be the filter stage, the power factor correction stage, and some sort of a isolated DC to DC converter. Now, the point of filter is to just clear out the waveforms to make them, to make them smooth. Maybe do some pre-charge, do some safe connection to the grid. Disconnected, there is a problem, and so on. Power factor correction is actually rectifying the free phase or one phase, correcting for the power factor, as the name suggests, to be compliant with the harmonic distortions and electromagnetic stuff. And the last stage is what provides the isolation, because every electric vehicle charger that's connected to the grid needs to be isolated from the grid. Now, I actually have all those parts in front of me, so you can just go quickly through them. This would be the filter. So just a quick introduction for that. The parts that you'll see in front of me are actually parts of a 25 kilowatt concept of power converters. There is more applications to them than just EV charging, and we supply these units, for example, for stationary DC chargers, or as people call them, the fast DC EV chargers, or maybe for some solar installation off grid and so on. Thanks to the higher efficiency of the silicon carbide, this technology has a lot of applications. But in this video, we're mainly going to focus on the EV charging, be it on board or stationary or portable. So now this is a filter module. It provides overvoltage protection, relays, pre-charge, two-stage filtering, and also carries all the digital signal processing on board to do everything, and it's just controlled over CAN bus and 24 volt and interlock. So this is a three-phase module, and it's meant for 25 kilowatt operation. You see here you have the input, here you have the output, three-phase in, three-phase out. So this is very simple. There are no active devices like transistors or anything. Now we're getting to the first active stage, which is the power factor correction stage. So at the end, you could think of this as the AC to DC converter, which starts as a rectifier, followed by a boost converter, which runs the power factor correction algorithm. Now, just like the filter module, the PFC is carrying all the digital signal processing on board, all the isolation of the low voltage signals, all the processing and everything. And the only interface that's here is the CAN bus and 24 volts. So all the modules can be chained, can be put into parallel and so on. Now, again, this is a 25 kilowatt unit, and here you have the inductors. Here you have the rectifier, and here you have the actual transistors. Now, as you can see, it's designed for flat mounting to make it very easy to mount either on a cold plate, which is water cooled, or maybe air cooled, just to give a bit more flexibility to our customers. So this is the power factor correction stage. On the input you would have 3-phase, and on the output you would have let's say 750 volt DC, which is already corrected for which already corrects for the power factor and so on. Now the following stage is a resonant DC to DC converter, isolated, which is this module. As you can see, it's bigger than the boost because it actually has to provide the isolation. And this is also a resonant converter, which makes it even slightly more complicated. Now, as you can see the holes, this is where the transformers go and also where the inductors will go. I have them removed so I can just hold it easier in my hand, but I'm going to show you them in a second. Now, just like the power factor correction stage and filter, this module carries everything it needs on board, from the low voltage power supplies, digital signal processing, communication, gate drives, everything. This just makes the module usable in different configuration, not necessarily as a part of an EV charger, but you can use it even standalone. Every module can be used standalone for different purposes. Now if you just look how it's constructed, so here you would have the input. Here you would have the digital signal processing, gate drive and so on. Here you have the 3-phase transistor bridge. Here under this place you will have the resonant inductors. Here you have the transformers. Here is the rectifier, the output filter and measurement. Now you can see from the other side. Now on this module, just like the power factor correction stage, it's fully based on silicon carbide, both the transistors and the rectifier, and it's actually what's called the 3-phase LLC. So it takes the 750 volt DC, chops it again into AC, runs it through the transformers and through the resonant circuit, and rectifies it again to DC. Now, this unit operates between, let's say, 200 to 350 kilohertz, so that's relatively high frequency switching, and again that's allowed thanks to silicon carbide. With IGBTs you can't really achieve such high frequencies without suffering huge conversion losses. Now if you look on the inductors and transformers, they're actually here. So this is a potted channel with the resonant inductors. And this is the potted channel with transformers. Now what I'm holding in my hand is a 25 kilowatt transformer carrier that actually works from this 750 volt DC to 400 volt DC, and that's the standard voltage that most cars run on. You can also replace this for any other voltages, so you could theoretically support 700 volt cars and so on. And as you can see, it's fairly compact. Thanks to the high switching frequency. If you ever seen the transformer stations for 50 Hz, you know how big difference there is between high frequency and low frequency transformers in size and weight. Now, what are we missing? Yes, if you use these 3 modules together, like they are on the table here, you can pretty much build an EV charging station or maybe a portable DC EV charger, or an onboard charger for maybe construction vehicles or any other application where you need to charge your batteries from the grid. And what's interesting about it, let's just move this module for the side. It's not part of the system, or at least for this one. What's interesting about it is the efficiency. So a standard EV charger that you would find maybe on the road when you're traveling on a highway, or you might find in your own electric car, usually has an efficiency of between 92 to 94%. That's fairly typical these days. This charger has an efficiency of 97%. Now you might think 93, 94 to 97, it's very similar numbers. What you need to think about is the losses. So the difference between 93 and 97 is actually that we have half the losses compared to the other charger. And this means you only have to dissipate half the heat, which means the charge can be very small. So what you're looking here at is 25 kilowatt charger station. You can put 2 in parallel, you have 50 kilowatt, you put 4, you get 100 kilowatt. Of course, the cooling, you cannot forget about the space that the cooling will take, but even the cooling will take less space than in a standard charger. So it's a fairly compact solution. Theoretically, if you designed it well, you could lift a 50 kilowatt charger as one person. I dare you to do that with the EV stations you find on the highway. Probably not going to be able to lift that even with 2 or 3 people. Now, the last module you see on the table is also a module of the same series. The whole series of these power converters is called MCP25. And this module in particular is actually a step-down module. So it's a DC to DC module that takes input voltage and steps it down. Now, what would this be good for? Imagine you have, for example, stationary batteries, and you would like to charge an electric car from stationary batteries, or maybe you have a solar installation that you would like to connect to your batteries, or maybe you have some other application that maybe requires, for example, battery to battery testing. Now, with this module, you can do that. You would have on the input, for example, let's just rotate it to make it easier for me to point out. So here is the input. As you see, 2 terminals for the DC. You could have, for example, 700 volt battery on the input, and you can have anything from 0 to 700 volt on the output at 25 kilowatt power, in case that you match it well enough with voltages. As an example, you could have a 700 volt battery on the input, 400 volt battery on the output, so it could be a vehicle, and you would get a 25 kilowatt charging system, and you can put as many of these as you want. I would say easily up to half a megawatt. Right now, the biggest installation we have out of these modules is 300 kilowatts. Now, another nice thing about this module is that it has a heatsink attached to it. So you get a feel for how the heatsink might look like. I'm not saying this is the best one. You can use water cooling, you have other options. But it kind of demonstrates what kind of efficiency we're talking about here. This is 25 kilowatt, has a 99% efficiency. That means at 25 kilowatts you would have only 250 watt losses, which this heatsink is for. So it's pretty small, and that really makes it possible to pack a lot of power in one package. For example, if you have the units in parallel. Now, the last module you don't see here is the charge controller. So we have a series of charge controller modules for DC charging, which is the CHAdeMO and CCS mainly. So we have charge controllers for both stations as well as vehicles, and that will be actually part of its own series. I'm not going to talk about that for now, but hopefully it's coming. Alright, so that would be all for today. So please do let me know what you think. If you have any comments, please put them down below. I'm also going to link our website and some other information. And well, if you have any questions, don't hesitate to contact us. Maybe if you have some projects, let us know, and we'll see if we can help you in any way. Have a nice day.